Welcome! In this session, we're diving into LeetCode problem number 914, X of a kind in a deck of cards. This is an interesting problem where we'll analyze whether a deck of cards can be grouped into subsets of a specific size. Stick around as we break it down step by step and explore efficient ways to solve it. In this problem, you are given an integer array called deck, where each element represents the value of a specific card in the deck. The task is to determine if it's possible to partition the entire deck into one or more groups of cards. If such a partition is possible, the function should return true, otherwise, it should return false. Each group must meet two specific criteria. First, every group must contain exactly X cards, and second, all the cards within a group must have the same value. The input is this array of integers, and the output is a Boolean value indicating whether the described partition can be achieved. Let's take a look at an example to illustrate this. Suppose the input is the array 1, 2, 3, 4, 4, 3, 2, 1. Here, the output is true. Why? Because the deck can be divided into groups where each group contains exactly two cards, and all cards in each group have the same value. For instance, we can form the groups 1, 1, 2, 2, 3, 3, and 4, 4. All of these groups satisfy the two conditions: they each contain two cards, and all cards within each group have the same value. Therefore, the partition is valid, and the result is true. Now, consider another example where the input is 1, 1, 1, 2, 2, 2, 3, 3. This time, the output is false. The reason for this is that it's not possible to divide the deck into groups of the same size where all cards in each group share the same value. While some groups can be formed, such as 1, 1, 1, or 2, 2, 2, there's no valid group size that works for all the cards in the deck. Therefore, the partition fails, and the function returns false. What about a case where the deck contains only one card? For example, if the input is 1, the output is false. This is because forming a valid group requires at least two cards in each group, as X must be 2 or greater. With only a single card available, it's impossible to create a group that meets the criteria, so the result is false. Finally, let's highlight some additional considerations for this problem. First, when the deck contains multiple cards but no valid group size exists, the function should return false. Second, if all the cards in the deck are identical, then it's always possible to divide them into groups of any size X that evenly divides the total number of cards. To determine if a valid partition is possible, the key lies in calculating the greatest common divisor, or GCD, of the frequencies of all unique card values in the deck. This ensures that the group size X is consistent and meets the required conditions. To solve LeetCode problem number 914, the main goal is to determine if the given deck of cards can be partitioned into groups of size X, where X is at least 2, and each group contains cards of the same value. One possible approach is the brute force method, which involves testing all potential values of X from 2 up to the size of the deck. For each X, we check if the deck can be evenly divided into groups of that size, ensuring all groups contain only cards of the same type. This is done by counting the frequency of each card using a hash map and verifying divisibility for each X. However, this approach has a time complexity of n*sqrt m, where n is the size of the deck, and m is the maximum card count. Due to repeated divisibility checks, this method is inefficient for larger decks. A more efficient approach leverages the greatest common divisor, or GCD. The key insight here is that for the deck to be divided into groups of size X, each card's frequency must be divisible by X. This means X must be a divisor of the GCD of all frequencies. If the GCD of all frequencies is at least 2, then partitioning the deck is possible. This observation forms the basis of our optimized algorithm. The optimized algorithm begins by counting the frequency of each card using a hash map. Once we have the frequencies, we compute the GCD of all these values. If the GCD is greater than or equal to 2, it indicates that the deck can be partitioned into valid groups, and we return true. Otherwise, we return false. The implementation for this approach can be written concisely in Python using the counter class from the collections module to count frequencies, and the GCD function from the math module combined with reduce to compute the overall GCD. This method has a time complexity of n plus k*log, max_f, where n is the size of the deck, K is the number of unique cards, and max_f is the maximum frequency. The space complexity is O, K. While there's an alternative approach using prime factorization, which involves breaking down frequencies into their prime factors and identifying a common factor, it adds unnecessary complexity. The GCD-based method is both simpler and more efficient, making it the preferred strategy. The GCD-based approach is the best solution for this problem for several reasons. First, it uses mathematical properties of divisors to simplify the problem, reducing it to computing the GCD of card frequencies. This eliminates the need to test every possible group size, making the solution more efficient. It has a time complexity of O, n plus k asterisk log, max_f, which performs well even for larger inputs. Additionally, the implementation is concise and easy to understand, making the code cleaner and less error-prone. When comparing strategies, the brute force approach, while straightforward, is inefficient for large decks due to repeated divisibility checks across all potential group sizes. The GCD-based method avoids this inefficiency by directly determining the largest possible group size using the GCD. On the other hand, the prime factorization approach, though theoretically valid, introduces unnecessary complexity without adding any practical benefits. Ultimately, the GCD-based method strikes the right balance between efficiency, simplicity, and correctness, making it the most suitable choice for solving this problem. This problem asks us to determine whether a given deck of cards can be divided into groups of size x, where x is at least 2, and all cards within each group have the same value. To solve this, we start by counting the frequency of each unique card in the deck. This step is crucial because the frequency of a card tells us how many times it appears, and grouping is only possible if these frequencies allow for equal-sized partitions. Using Python's counter from the collections module, we can efficiently calculate these frequencies in one pass through the deck. Once we have the counts, we extract these frequency values into a list. This gives us a clearer picture of the distribution of cards, which lays the foundation for determining if a valid partitioning is possible. Now that we have the frequencies, the next step is to compute the greatest common divisor, or GCD, of these values. The reason this step is important is that the GCD represents the largest number that can evenly divide all the frequencies. If the GCD is at least 2, it means we can partition the deck into groups of that size. To compute the GCD, we use Python's math.gcd function. If there are multiple frequencies, we calculate the GCD iteratively, combining one pair of frequencies at a time. After computing the GCD of all frequencies, we simply check if it is greater than or equal to 2. If so, the deck can be partitioned into valid groups, and we return true. Otherwise, if the GCD is less than 2, no valid partitioning is possible, and we return false. This approach is both efficient and grounded in mathematical principles, allowing us to avoid brute forcing all potential group sizes. Let's take a closer look at the data structures and operations involved in this algorithm. We use a counter to calculate card frequencies in linear time, O, n, where n is the size of the deck. The frequency values from the counter are then stored in a list, which simplifies the GCD computation. For computing the GCD, we rely on the Euclidean algorithm, which operates in O, log, min, a, b, time for two numbers. Extending this to a list of k frequencies involves pairwise GCD computations, resulting in a total complexity of O, k asterisk log, m, where k is the number of unique card values and m is the largest frequency. Additionally, we need to consider edge cases. For example, if all cards are identical, the GCD equals the total number of cards, making partitioning straightforward. On the other hand, a deck with just one card or prime frequencies that share no common divisor greater than 1 would make valid grouping impossible. Even an empty deck returns false since no groups can be formed. These cases highlight the robustness of the algorithm in handling various scenarios. Finally, let's analyze the overall complexity and walk through an example to solidify our understanding. The time complexity of this algorithm is O, n, for counting frequencies, and O, k asterisk log, m, for computing the GCD, making the total complexity roughly O, n plus k asterisk log, m. The space complexity is O, k, as we store the frequency counts for k unique card values. Now, consider the input deck, 1, 1, 2, 2, 2, 2. First, we count the frequencies, resulting in 1, 2, 2, 4. Next, we extract these frequencies into a list, 2, 4. We then compute the GCD of 2 and 4, which is 2. Since the GCD is at least 2, we conclude that the deck can be split into groups of size 2. The output is true, showing that partitioning is indeed possible. This example demonstrates how the algorithm works step by step, validating its efficiency and correctness. This solution aims to determine whether it is possible to partition the given deck of cards into groups of size x, where x equals 2, with each group containing cards of the same value. Explanation of the code. 1. Imports. The counter from collections is used to count the frequency of each unique card in the deck. The GCD function from the math module helps compute the greatest common divisor of the frequencies. 2. Counting frequencies. The counter, deck, creates a dictionary-like object where the keys are the unique cards, and the values are their frequencies in the deck. 3. Computing GCD. We initialize G to 0. Then, for each frequency in the counter, we compute the cumulative greatest common divisor, GCD, of all frequencies. This is done iteratively using GCD, G, frequency. For checking partition feasibility, after computing the GCD of all frequencies, if the GCD is at least 2, it is possible to partition the deck into groups of size x, where x equals GCD. If the GCD is less than 2, partitioning is impossible. 5. Return statement. The final result is true if the GCD is 2 or more, and false otherwise. Complexity analysis. Time complexity. Counting the frequencies takes O, n, where n is the size of the deck. Computing the GCD iteratively for k unique cards takes O, k asterisk log, max underscore frequency, where max underscore frequency is the highest frequency. Overall complexity is approximately O, n plus k asterisk log, max underscore frequency. Space complexity. The counter object uses O, k, space, where k is the number of unique cards. This implementation efficiently handles edge cases, such as decks with only one unique card or decks where all frequencies are coprime. Here, we start by importing the necessary Java utilities and defining our solution class. The method hasGroupSizeX takes an integer array deck as input, representing the cards. Our goal is to determine if it's possible to group these cards into one or more groups of the same size, where each group has exactly the same number of identical cards. First, we use a hash map to count the frequency of each card. By iterating through the array, we update the map with the count of each card using getOrDefault, a convenient method to handle default values. Next, we need to determine the greatest common divisor, or GCD, of all these frequencies. To do that, we initialize a variable GCD value to 0 and update it iteratively for each frequency in the map. This ensures that we calculate the GCD of all card frequencies in the deck. Finally, we check if the GCD is greater than or equal to 2, because a GCD of at least 2 indicates that we can form groups of that size. If so, the method returns true, otherwise, it returns false. We've also defined a helper method GCD to calculate the greatest common divisor using Euclid's algorithm, which we'll look at next. The helper method GCD is implemented using Euclid's algorithm, which is an efficient way to compute the greatest common divisor of two integers. The method takes two input parameters, a and b. While b is not 0, we repeatedly update b to the remainder of a divided by b, and a to the previous value of b. This process continues until b becomes 0, at which point a contains the GCD of the original two numbers. Finally, we return a as the result. This helper method is essential for our main logic, as it allows us to compute the GCD of all card frequencies in an efficient and iterative manner. Together, the hasGroupSizeX method and the GCD helper form a complete solution to determine if the deck can be partitioned into valid groups. This problem challenges us to determine if a deck of cards can be grouped into sets of size x, where x is at least 2, and each set contains identical cards. For example, with the input deck 112222, the first step is to count how many times each card appears. Using Python's collections counter, we find that card 1 appears twice and card 2 appears 4 times, giving us the frequency count 1, 2, 2, 4. Next, we calculate the greatest common divisor, or GCD, of these frequencies. To do this, we initialize the GCD, G, as 0. We then process each frequency one by one. The GCD of 0 and 2 is 2, so G becomes 2. Then, the GCD of 2 and 4 is also 2, meaning G remains 2. The final GCD of all frequencies is therefore 2. Now that we've calculated the GCD, the next step is to check whether it is at least 2. In this case, G equals 2, which satisfies the condition, so the deck can indeed be grouped into sets of size 2. The output for this example is true. Let's explore another example. With the input deck 1 1 1 2 2 2 3 3, we start by counting the frequency of each card. This gives us 1 3 2 3 3 2. To compute the GCD of these frequencies, we again initialize G as 0. The GCD of 0 and 3 is 3, so G becomes 3. Next, the GCD of 3 and 3 is still 3, so G remains unchanged. Finally, the GCD of 3 and 2 is 1, meaning the final GCD of all frequencies is 1. With a final GCD of 1, we check whether it meets the condition of being greater than or equal to 2. Since 1 is less than 2, this deck cannot be grouped into valid sets, so the output is false. Now, consider the input deck 5 5 5 5 5 5 5 5, where the frequency count is 5 8. Here, we calculate the GCD of the frequencies, starting with G initialized at 0. The GCD of 0 and 8 is 8, so G becomes 8. This means the final GCD is 8. Since 8 is greater than or equal to 2, we can group this deck into sets of size 8, or even smaller sizes such as 4 or 2. The output for this example is true. To analyze the time complexity of our solution, we can break it down into distinct steps. First, we count the frequencies of each card in the deck using the counter class from the collections module. Since we iterate through the deck once to build the frequency dictionary, this step takes linear time, or n, where n is the size of the input deck. Next, we look at the process of iterating through the frequencies. The count.values method gives us a list of these frequencies, and we have k unique frequencies, where k is the number of unique cards in the deck. For each frequency, we calculate the greatest common divisor, or GCD, using Python's GCD function. The GCD calculation uses the Euclidean algorithm, which has a time complexity of O log min a b for two numbers a and b. If we consider all k frequencies, the total time spent on GCD computations is O k asterisk log max frequency, or max frequency, is the highest frequency among the cards in the deck. Next, we consider the final step of the algorithm. Once we've computed the overall GCD of the frequencies, we perform a simple comparison to check if the GCD is at least 2. This is a constant time operation, O1. Now, combining all the steps, the dominant time complexities are O, n, for counting frequencies and O, k asterisk log, max, frequency, for computing the GCD. Since k, the number of unique cards, is at most n in the worst case, the overall time complexity is O, n plus k asterisk log, max, frequency. This simplifies to O, n plus n asterisk log, max, frequency, in the worst case scenario, where every card in the deck is unique. This demonstrates how the algorithm efficiently handles even large inputs by focusing on the most critical operations. Let's now analyze the space complexity of our solution. The primary contributor to space usage is the frequency dictionary created by the counter. This dictionary stores the frequency of each unique card, so in the worst case, where all cards in the deck are unique, it will have k entries, where k equals n. This gives us an O, k, space complexity, which simplifies to O, n, in the worst case. Additionally, we use a small number of integer variables, such as g for tracking the GCD and frequency for individual frequencies. These require constant space, O1. Combining these factors, the overall space complexity of the solution is dominated by the frequency dictionary, resulting in O, k, or O, n, in the worst case. This ensures that our solution remains space efficient, even for large decks. When comparing the optimized solution to a brute force approach, the performance benefits become clear. A naive solution would involve iterating over all possible group sizes x, from 2 to n, and checking if the deck can be partitioned into groups of that size. This would require multiple passes over the deck for each potential group size, leading to a worst-case time complexity of O, n squared. In contrast, the current solution leverages the mathematical properties of the GCD to determine the largest common divisor of group sizes. This reduces the time complexity to O, n plus k asterisk log, max, frequency, which is significantly faster for large inputs. From a space perspective, both approaches require O, n, space for storing counts, but the optimized solution clearly outperforms in terms of time efficiency. The breakdown of operations, like counting frequencies in O, n, and computing the GCD in O, k asterisk log, max, frequency, justifies the final time complexity, making it ideal for handling large decks. Finally, let's evaluate the time complexity across best, average, and worst-case scenarios. In all cases, we spend O, n, time counting frequencies, as each card in the deck is visited once. The time spent on GCD computation depends on k, the number of unique cards, and max, frequency, the largest frequency value. However, these factors do not change the asymptotic complexity, which remains consistent across all scenarios. Whether the deck contains identical cards, a mix of repeated and unique cards, or all unique cards, the algorithm's performance is governed by the same O, n plus k asterisk log, max, frequency, time complexity. This consistency ensures that our solution is robust and efficient, regardless of the input distribution. When solving this problem, there are some common mistakes you should be aware of. First, make sure that the value of x is at least 2. Returning true for x equal to 1 violates the problem's requirements, since we need groups of 2 or more. Next, don't assume that simply finding the GCD of the frequencies is enough. You also need to verify that the GCD can divide all frequencies. Overlooking edge cases is another frequent issue. For example, you might encounter situations like a single card in the deck, multiple cards of the same value, or even an empty deck. Test cases like 1, 1, 1, 1, 1, and ensure your solution handles these scenarios correctly. Additionally, inefficient frequency calculations can slow down your solution. Instead of nested loops, use a hash map or Python's collections counter for a more optimal approach. Finally, pay close attention to the constraints. The total number of cards must be divisible by x, so double-check this condition to avoid logical errors. Now let's delve into some insights that are particularly valuable for interviews. One key takeaway is the connection between the greatest common divisor, or GCD, and group sizes. The GCD of all frequencies essentially determines the largest possible value of x that meets the problem's conditions. Recognizing this relationship is crucial. This problem also evaluates your ability to recognize patterns and translate real-world scenarios, like grouping items, into mathematical properties. Practicing problems involving divisibility or modular arithmetic can help sharpen this skill. From an interviewer's perspective, they're looking for optimal thinking. Highlight how you simplify the problem using the GCD to reduce complexity. Additionally, discussing edge cases during an interview demonstrates your thoroughness. Make sure to mention inputs like empty decks or scenarios where all cards are of the same type to show that you've thought through every possibility. This problem also shares similarities with other challenges you might encounter on LeetCode. For instance, LeetCode 242, Valid Anagram, tests your ability to count frequencies efficiently, which is a core skill here as well. Another related problem is LeetCode 202, Happy Number, where modular arithmetic and mathematical reasoning play key roles. LeetCode 1025, Divisor Game, involves reasoning about divisibility, which ties into the concepts we've discussed. Lastly, LeetCode 1071, Greatest Common Divisor of Strings, applies the GCD in a string-based context. Exploring these related problems can reinforce your understanding of the techniques and patterns involved, while also providing a broader perspective on how these concepts are applied in different scenarios. There are also alternative approaches to solving this problem, each with its own trade-offs. A brute force approach involves iterating through all possible values of x, from 2 up to the deck size, and checking divisibility for each. While this method is simple to implement, it's computationally expensive, with a time complexity of O, n squared, making it impractical for large inputs. A more efficient solution leverages the GCD. Using a hash map to count frequencies, you can compute the GCD of all frequency values and then verify if it's greater than or equal to 2. This optimized approach reduces the time complexity to O, n log k, where k is the range of card values, but it does require a solid understanding of the GCD and its properties. Lastly, there's a less common approach involving prime factorization. By factorizing the frequencies, you can check if they share common prime factors for divisibility. While this method is more complex and rarely used, it's worth mentioning as an advanced option for specific scenarios or deeper exploration of the problem. Great work! To summarize, we used the GCD to check if the deck could be partitioned into groups of size X. We explored hash maps for frequency counting and analyzed its efficiency. Don't forget to practice similar problems to solidify your understanding, and thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!